All right, folks. Well, let's continue on with the video today. I was happy to see everyone was doing well in class today. Um, I do want to make sure I remind you folks, though, please make sure you watch the videos. I know today in class we went over it, we reviewed a little bit. So let me go ahead and let me get started. Let me start the timer so I don't go shoot over the my time limit. Okay. But I do want to remind everyone to please make sure then that you keep you watch those videos, and that way then when we start our discussion today, um, and then continue it on Thursday, you'll be able to keep up with the discussion. Okay, please make sure you ask your questions as well. Don't hesitate to ask. Um, don't wait. Don't wait to ask. Because what'll happen is that the confusion will just start to mount, and it'll just pile on top of one another, and it'll make it very difficult for you to be able to keep track of what we're discussing. Okay, so please make sure you keep up with the work and get the work done. Okay. All right, so what I'd like to do then, so we reviewed today acids and bases. We worked through a problem, worked through a couple of homework problems that kind of reviewed for us and helped us to identify the acid and base, helped us to review acid equilibrium and how we set up the law of mass action for the acid dissociation constant. We talked about autoionization of water. You got to make sure you keep that in mind because that'll be important as we move forward today in this lecture as well. So please make sure you keep track of that and review that or take a look at it and make sure that you understand what that is. Okay. And if you need to, again, come by and see me. I am available tomorrow from after exam to about 11 o'clock to take your questions. Okay. And I'll be available on Thursday as well after school, after my 7th period class to take your questions as well. Okay. So please make sure you take advantage of those opportunities. Okay. All right, so what I would like to do then is to review what we talked about in the last video, in the last lecture video. I want to go ahead and do a couple of homework problems. No one asked about this, but I want to go ahead and do the homework problems here to help you review how we deal with hydrogen ion concentrations, how we deal with Kw, the value, how we describe Kw, and then also how we can use that in order to calculate for the hydrogen ion concentration hydroxide ion concentration. Okay, so we saw today, you guys, so let's make sure we keep this in mind. We saw today that we can identify an equilibrium constant known as Kw, and we saw then the Kw, and I'm just going to go the shorthand way, you guys. So Kw then we saw that is the concentration of the hydrogen ions times the concentration of hydroxide ions. We typically call this the ion product constant as well. Water ionization product constant as well. And we saw then that that is going to be equal to 1 times 10 to the minus 14. This is a constant. That means this number does not change. Which means then if we, and I reviewed this with you, if we are at a neutral solution, we should have then equal concentrations here. You can see then how we can get that concentration, because if we have equal concentrations, then both of these, if they're unknown, will be X. Okay, so let's go ahead and just do that real quickly. And that will be equal to 1 times 10 to the minus 14. In which case, then, if you solve for this one, and I'll leave it up to you to solve for it. If you solve for this one, then you'll see then that X is going to be equal to 1 times 10 to the minus 7. That would be for a neutral solution, right? So that's how you go about solving for. So let's say then that we don't have a neutral solution. That means that we have a solution in which we know either the hydrogen ion concentration and hydroxide ion concentration, and we know that it's not 10 to the minus 7. Well, you can imagine we just set up we start out with this equation here. So we will always start out with this equation. If we need to solve for the hydrogen ion concentration, hydroxide ion concentration, we start out with this equation here. And from this, we can solve then for one of the missing components. It ends up being a simple algebraic problem. All right, so let's go ahead and let's take a look at, let's go ahead then, let's do number 45. Okay, and I'm going to work on number 45 okay, in your book. Okay, so number 45 from the textbook, which is on page 703. Okay, so go ahead and grab your book really quickly, pause the video if you need to, grab your book. And what I would like you to do on your paper, okay, so on your paper, what I like, A, I'm not going to do for you. Hopefully you can do A. I hope that you can do A. Okay? What I'd like you to do then is take a couple of minutes to work out B. So on your paper right now, okay, I'd like you to work out number 45B, and then we'll talk about it. Okay, so take about 3-ish minutes, okay, to work out 45B, and then we'll meet back, and then we'll go over. Okay, so go ahead and take about 3 minutes to work on number 45B. Okay, well, hopefully you got that done. So in 45B, let's go ahead and let's take a look at this. We are given the hydrogen ion concentration. We are told then, oh, sorry, hydrogen ion concentration. We are told then that the concentration of the hydrogen ion is 8.3 times 10 to the minus 16. So hydrogen ion concentration is going to be equal to 8.3 times 10 to the minus 16. Okay, molar. Okay, let's do this first. They ask us to identify whether this solution, whatever this solution is that solution an acid solution, a base solution, or is it a neutral solution? And without having to do any calculations, we should be able to do that. Okay? Because let's go ahead and let me give you the summary for this again. Okay? We know then for a neutral solution, for a solution that is considered neutral, okay, what are the key features of a neutral solution? Well, we know then the one key feature that we need to recognize for a neutral solution is that the hydrogen ion concentration and the hydroxide ion concentration, both of those are equal to one another, and both of those will be equal to 1 times 10 to the minus 7 molar. And you hopefully were able to get that from 45A and from our discussion here. So that's for a neutral solution. That's the first thing you have to keep in mind. For an acidic solution then, for a solution that is considered acidic, means it has acid, it is an acid, okay? We know this, okay? We know then that the hydrogen ion concentration cannot be equal to 10 to the minus 7, but it has to be greater than 1 times 10 to the minus 7 molar. So if a solution is acidic, the hydrogen ion concentration is greater than 1 times 10 to the minus 7, which means then the hydroxide ion concentration has to be less than 10 to the minus 7 molar. Because again, if Kw is constant, if the water dissociation constant, ion product constant for water is 1 times 10 to the minus 14, and that's a constant, and that constant is determined by the product of these two here. As one goes up, these are, if you look at it, that what we're saying is these are inversely related. As one gets larger, the other one has to get smaller. So as hydrogen gets larger than 10 to the minus 7, hydroxide has to get smaller times 10 to the minus 7. Okay? So that's why these are the conditions here. These are the two conditions for, and you have to you don't have to identify both. Just identify one. Because if one is greater than 10 to the minus 7, the other has to be less than 10 to the minus 7. Okay? So if you notice here then, the hydrogen ion concentration, I'm sorry, let's go ahead and do the last one for the basic solution. I get a little bit ahead of myself. Okay, so for a basic solution then, a solution that is considered a base, okay, we know then that the opposite has to be true. That in this case then, the hydrogen ion concentration will be less than 1 times 10 to the minus 7 molar, and the hydroxide ion concentration will be greater than 1 times 10 to the minus 7 molar. So keep this in mind. Keep this general summary in mind right here. Use this to your advantage here to help you determine then the acidity or basicity of a solution. So looking at our concentration here, we are given a hydrogen ion concentration of 10 to the minus 16. That is a whole lot less. That is a whole lot smaller than 10 to the minus 17. So we already know off the bat, you guys, that this solution is a basic solution without having to determine the hydroxide ion concentration. We already know that this is a basic solution based on the hydrogen ion concentration here and based on what we memorized right here. Okay. All right. So with that said, then they do want us to calculate the hydroxide ion concentration. So we know that this is true. Okay. We know then that we have the hydrogen ion concentration. Okay, so we know the hydrogen ion concentration. So hopefully you can rearrange this here to get that. So if we divide the hydroxide ion concentration, which we will refer to as, if you want to write it as X, you can. But that's our unknown. Okay? You'll see then that if we divide both sides by the hydrogen ion concentration, we're going to get hydroxide ion concentration. And that's it. That's it, you guys. That's how simple these problems can be. Okay. All right, so plugging that in, we have 1 times 10 to the minus 14 divided by the hydrogen ion concentration of 8.3 times 10 to the minus 16. And if you work that out, you punch it into your calculator correctly, you will get 12 as the hydrogen ion concentration. The concentration of hydrogen ion is 12, and that is huge. That's a huge concentration. That is a massive concentration that is much, much larger than 10 to the minus 7. And that's why this solution is also a basic solution. Okay. So given, if we can measure this here, which we can, we have a pH meter, we have ways that we can obtain the hydrogen ion concentration, we get this value here, we can determine the concentration of the hydroxide ion concentration, we can determine the concentration of hydroxide ions by a very simple calculation. Okay, so this can be a measured value here, and based on this measured value, we already know that this solution will be basic. So if you were to take, let's say, litmus paper, you put it in there, you can see that that litmus paper is going to turn a very dark purple color. If you had used red litmus paper, and if you had used blue litmus paper, it wouldn't have turned colored, wouldn't have changed colors at all. Okay. All right. Let's go ahead then and let's do another one. Okay, let's do another one. Let me ask you. I'll leave C for you to do. Let's do 45D. Okay. So take about 3 minutes and work out number 45 D. Okay. On your paper that you'll submit, work out 45D. Okay. So take about 3 minutes to work that out. Okay, 45D, let's go ahead and let's take a look at this. This time, 45D, we were given a hydrogen ion concentration of 5.4 times 10 to the minus 5 molar. Okay. This time then, this is the hydrogen ion concentration. Based on our summary right here, you guys, based upon what we are given right here, we know then that this number here is about 100 times greater than this number. So the hydrogen ion concentration this time is greater than 10 to the minus 7. So we already know before we have to do any calculations that this is going to be an acidic solution. This is going to be a solution that has acid. It is going to be an acid solution. That's what we know. Okay. All right. So going ahead then and calculating for the hydroxide ion concentration, we're going to do the same thing. It's going to be Kw over the hydrogen ion concentration. And that's going to be then 1 times 10 to the minus 14. This time it's going to be over 5.4 times 10 to the minus 5. And we get our answer here as 1.9 times 10 to the minus 10 molar. Okay. All right. And as you notice here, that concentration is much less. It's much smaller than the concentration of 10 to the minus 7. Then this is a basic solution. Okay. All right. Last thing I want to point out to you guys then is let's make sure we remember significant figures. Okay, we have 2 significant figures in the number here. We should have 2 significant figures here in our answer. 2 significant figures in our original measurement here. We should have 2 significant figures here. Okay, so make sure then that you are aware of sig figs as well. Because remember with the pH, when we start talking about pH in just a moment, the pH, the significant, how we determine significant figures for pH is a little bit different. You got to practice it. You got to practice it, but it is a little bit different from what we have here. Okay. All right. So if you have questions on this problem, please make sure you ask on Thursday. You ask on Thursday, and I'll go over a few more of it, and then I'll talk about it with you. Okay. So, but let's continue on. Okay. I'll save this for you. But let's continue on. Let's do another set of problems here. Let me go ahead and I'm going to erase this here. Okay. And let's take a look at what pH is. Okay. So let's take a look at what this term pH is supposed to mean. The term pH, the reason why we use pHs in the first place is so that we have a scale that we can use to measure the acidity or the basicity of a solution that is not going to be a very small number. It's not going to be a number that is less than 1. Okay? However, so with that said, then the scale then will allow us to obtain numbers that are a little bit larger, a little bit easier to handle. Okay, typically the pH scale the pH scale range in order from 0 to 14. So 0 being acidic. Okay, so this is the acidic side. Okay, and the 14 then being the most basic. Okay? So we get as the pH scale goes up, you get more a more and more basic solution. Okay, with 7 then, and we talked about this, 7 representing then a neutral solution. So right in the middle, we have then a neutral solution. Okay, so acid below 7, basic above 7, 7 is going to be neutral. Okay, all right. So that's the pH scale. Can we get pHs less than 0 on the negative side? Theoretically, yes, but in reality, no. In practice, no. Can we get pHs that are above 14? Theoretically, yes. In terms of real life and practically, no, we won't get this. So typically, you will see solutions with pH between 0 and 14, and that's it. Okay. All right. So how do we get this pH scale? Okay. Well, remember, we said then that this P here in the last video, we said this P here is a mathematical operator that tells you to take the negative log of whatever follows it. H here then represents then the hydrogen ion concentration. So whenever you see the pH, it's telling you then to take the negative log of the hydrogen ion concentration. Which means then, if you see this here, that if you see the term POH, it's reminding you that how we obtain that is by taking the negative log, this time, of the hydroxide, OH concentration. Okay? If you see pKW, that means then we want to take the negative log of the ion product constant for water. If you see pKa, that means that we're taking the negative log of the Ka value, and so on and so on. And so you get the idea. I hope you get the idea. For our purposes, this P then, the letter P, is an operator that tells you to take the negative log of whatever follows it. Okay. All right. So that's what pH means. That's what the pH, how we pH, and that's what the rest of it means as well. Okay. We now know we remember then the pH scale right here. And so with that said, then let's take a look at what we saw then with the ion product constant. We saw then the ion product constant was the concentration of hydrogen ions times the concentration of hydroxide ions. And we saw that that's going to be equal to 1 times 10 to the minus 14. Okay. Taking the negative log of all this, then we get then the taking the negative log, doing the negative log of all this, we get pKW. It's going to be equal to then the pH. Negative log of this one's going to be plus the POH, and that's going to be equal to 14. Okay. And so with that said, then we have a way then to calculate for the POH and the pH if we want to in a much simpler manner. Okay. So make sure then that you keep this in mind, that all these here can help you. Solving for the pH, solving for the POH can be very, very simple. And so let's take a look at number 49. Let's take a look at number 49 and let's work that out. So number 49, they are asking us to go back and take a look at the what we did in 45. In number 45 on page, and this is, I'm sorry, number 49 on page 703. Okay? And they're asking us then to find the pH of each one of those solutions. So let's go ahead, and I'm going to leave A for you to do, you guys. Make sure you're able to do A. Let's go ahead and let's take a look at B together. Okay? So in B then, we were told then that the hydrogen ion concentration, remember from B, the hydrogen ion concentration there was 8.3 times 10 to the minus 16 molar. Okay? All right, and they want us to find the pH of this solution. Okay, so finding the pH of this solution, you guys, all we do is take the negative log. So the pH then is going to be the negative log of the hydrogen ion concentration. Okay, and so in this case, then we're going to plug in and don't forget the negative sign here, folks. Okay, this is the negative log, not just log. And so you take the negative log of 8.3 times 10 to the minus 16 molar. Okay, and so when you plug that in, you're going to see then that your answer ends up being, and let me go ahead and take a look at this really quickly, 15.08. Okay. So our answer then is 15.08 as our pH. And that is way off the scale here. And like I told you, in theory, can we get pHs that are greater than 14? Sure. And this is an example of a pH that is greater than 14. In practice, that means in real life, when you're in lab or when you're working with these chemicals, will you ever get a pH greater than 14? No, most likely not. Okay. All right. So with that said, then how do we find then the POH? Because I think in number 49 they want us to calculate the pH and POH of the solution itself. Okay. Well, we calculated for the hydroxide ion concentration. So remember from the problem that we did, we were able to calculate for the hydroxide ion concentration, and we were able to calculate the hydroxide ion concentration as being 12. With this hydrogen ion concentration, we have the hydroxide ion concentration here, which means then we can calculate for the POH. Okay, the POH, looking at our chart here, is going to be then the negative log of the hydroxide ion concentration. And in this case, then the hydroxide ion concentration is 12. So we take the negative log of 12 molar, and we see then that we get a value that is negative 1.08. Okay? And that is our POH. Okay? And in this case, then on the POH scale, we have a pH scale here, typically ranges from 0 to 14 as well. And here's an example of a POH that's going to be less than 0. Again, will you ever see this in real life, in practice, in lab? No. You're going to typically see pHs and POHs ranging from 0 to 14, nothing greater and nothing smaller. Okay. All right. So understand that this represents the POH and this is the pH. They are two different scales. Okay? The numbering is the same. How you calculate for them is the same, but they represent different things. This represents then the concentration of hydroxide ions in solution. This represents the concentration of hydrogen ions in solution. Okay. All right. So hopefully you're able to do that. Now, the last way that you can do this, again, like I said, if you understand this, we can find the POH here without having to do this calculation. Okay? And using what we know here about the pH and the POH and the pKw as being equal to 14, hopefully you can recognize then that we can solve for the POH by subtracting the pH from both sides. And you should and you will end up getting the same answer, which is 15.08. It's going to be negative 1.08 as your POH. And if you were able to calculate for the pH, you can go ahead and do the same thing and obtain the pH in that manner there. Because this is right here, this is the relationship between pH and POH. This is the relationship between hydrogen ion concentration and hydroxide ion concentration. This equation here is the relationship between pH and POH. Okay? All right. So let's go ahead. Let's talk real quick about significant figures here. Now, if you notice here in this particular answer, our problem here, we have two significant figures in our initial value measurement here. We have two significant figures here. Okay. However, when we get to our answer, our pH, our answer has four significant figures, 1508. The answer here has three significant figures. How are we supposed to go about doing this? Okay. All right. So remember, the rule for pHs then is that for the number of significant figures in our concentration, so we have two here. Okay, we are supposed to keep two decimal places. We are supposed to carry two decimal places for every. We're supposed to carry an equal number of decimal places for the number of significant figures. So if you have two significant figures, you need to carry two decimal places. If you have one significant figure, you need to carry one decimal place. So the number of decimal places here, so you have two decimal places, corresponds to the number of significant figures. That is how we determine the number of digits we're allowed to keep in our final answer for the pH or for the POH. Okay, so make sure you keep that in mind. It's an odd rule, it's a strange rule, but that's the one that we're using. Okay. All right, so let me ask you then, so that's number 49. Let me ask you to 49B. Let me ask you to finish up here. Let's do 49D. Okay, so on your paper, I'd like you to do 49D. Okay, so I just did 49B there for you. Take about, and I'll save this, let's take about 3 minutes to do 49D, and then I'll work it out with you. Okay, so 49D, go ahead and get that done. Okay, let's go ahead. Let me go ahead and let me erase this. Yeah, I'll leave everything up here, but let me go ahead and let me erase this. Let me erase all this work down here so that I have room to work out 49D for you. Let's go ahead and do 49D together. And make sure then, folks, check your work, and make sure then that if you got the right answer, good for you. If not, then please make sure then that you take a look at what you did compared to what I'm going to do here for you. and see what might have happened. Okay, and if you can't quite figure it out, again, please make sure you come by and see me and get some extra help with this. Okay, so let's go ahead then. Let's do 49D together. Okay, so let's go ahead and let me go ahead and write that down. So we're going to do 49D. Okay, and in 49D, then we start out with the hydrogen ion concentration of 5.4 times 10 to the minus 5 molar. Okay. All right. So with that said, then, and I'll just write down here for you. Also, we were able to calculate them for the hydroxide ion concentration of I think it was 1.9 times 10 to the minus 10 molar. Okay. All right. pH, calculated for the pH, pretty straightforward then, negative log of the hydrogen ion concentration. So the pH then is going to be the negative log of the hydrogen ion concentration, which in this case then is going to be the negative log of 5.4 times 10 to the minus 5 molar. Okay. Our final answer then, let's make sure we keep this in mind. Our final answer has to have, since there are two significant figures in our answer here, whatever our final answer is, has to have two decimal places. Okay. We have to make sure we include two decimal places there. So with that said then, you punch that into your calculator. I get then a value of 4.27. There it is. There are the two decimal places. Okay. So two significant figures, two decimal places. Okay. Our final answer then is 4.27. Okay. All right. Whoops. Sorry. Let me go ahead. Sorry. Wrong color there. Okay. So let's go ahead then. Let's take a look at the calculating for the POH. Okay. So the POH then, go ahead and we take then the hydroxide ion concentration, and we take the negative log of the hydroxide, the OH concentration. And the OH concentration in this case then is going to be 1.9 times 10 to the minus 10 molar. Okay. So therefore, the POH then, again, since we have two significant figures here, our POH should have two decimal places. And so I get here 9.73 as our answer for the POH. Okay. All right. Now, with that said, then again, you can use the relationship between the pH and the POH and the pKw in order to get their answers. So therefore, for the POH, then it'll be 14 minus the pH. In this case, then it's going to be 14 minus 4.27, which will give you 9.73 as well. So either way will work. If I ask you to do this calculation on the exam, in about a week, you can choose either one of these methods here to calculate for the POH. Okay? All right. Very good. Let me go ahead and save this for you as well. And so if you have any questions on this, please make sure you ask. Okay? So what I'd like you to do then is, now that we have done that review, what I'd like you to do is, let's take a look at number 10 in your problem set. Take a look at number 10 in your problem set and make sure you understand what they're asking you to do here. Okay? Number 10 in your problem set, they're asking you to find then the hydroxide ion concentration, very much like we did with the two problems from the homework. But look at the difference now. For number 10 here, they're asking you to find the hydroxide ion concentration given the pH of 5.85. So what I'd like you to do is take about 3 minutes, to work through this problem on your paper. Take 3 minutes to do number 10 on your paper. And then at the end of that time, I'm going to go over this with you. So take a look at number 10, work out, do the best you can with number 10 here on your paper, and then I'll work it out for you. 3 minutes, okay? All right, let's take a look at this, you guys. They want us to find the hydroxide ion concentration, but what they give us is the hydrogen ion concentration. They give us the pH. Now remember, the pH does not give us the hydroxide ion concentration. The pH, if we solve for it, if we take the inverse log, that is the inverse log, and make sure you keep that in mind, okay? Which is, find it on your calculator. You got to find that button on your calculator. Okay? If you do the inverse log of this, you're going to get the hydrogen ion concentration, not the hydroxide ion concentration. Okay? So, a couple of ways that you can go about working this out, you guys. A couple of ways. Hopefully, either way will work out fine. Okay? So, what we need to do is we need to get the POH. Okay? We need to get the POH. Okay? So let's go ahead then. We remember then that the pKw is equal to the pH plus the POH, which is going to be equal to 14. So let's go ahead and solve for the POH. Let's go and do that. So the POH then is going to be equal to 14 minus the pH, which in this case then it's going to, I'm sorry, which in this case then it's going to be 14 minus 5.85. Okay, and if you get the pOH there, that's going to give you 8.15. Okay, so that is the pOH. Okay, at this point we have the pOH, and remember the pOH is the is equal to the negative log of the hydroxide ion concentration. So therefore, if we take the inverse log of, and make sure you take the inverse log here, the pOH, okay, we should be able to get the hydrogen ion concentration, okay, hydroxide ion concentration. So let's go ahead, and this represents the negative log here. Or your calculator should either show as 10 to the x or as a negative inverse log. Okay, so make sure you keep that in mind. All right, so we plug that in, and you got to make sure then that you take the negative here, you guys. Okay, so it's going to be negative 8.15. Okay, 10 raised to 8, negative 8.15, and you'll get your answer then as 7.1 times 10 to the negative 9 molar. And that would be the hydroxide ion concentration. Okay, and so why two significant figures here? So remember, we're working backwards. Okay? We have 2 decimal places here. So this is 2 decimal places, which means then our answer must have 2 significant figures. Okay? So we kind of work backwards in that way. All right, so that's one way you can do it. That's one way you can do it, you guys. The second way that you can go about doing this then involves using not this relationship, but using what we know about the hydroxide ion concentration times the, the hydrogen ion concentration times the hydroxide ion concentration, that being equal to 1 times 10 to the minus 14. So in this case, then, we can solve for, now that we have the, so using this here, we got to get the negative log of the, we're going to use the negative log of the hydrogen ion concentration in order to find the hydrogen ion concentration. Okay, so the hydrogen ion concentration then is going to be then the negative log, which is going to be the inverse of pH. The negative log of the pH, 10 raised to the negative pH, which is going to be 10 raised to the negative 5.85. Okay. And if you punch that into your calculator, I forgot, let me go ahead and do that real quick here. Let me punch that into my calculator. Negative 5.85. I get 1.41. So this is going to be 1.4 times 10 to the minus 6 molar. Right? So there's your hydrogen ion concentration, you guys. So you find the hydroxide ion concentration based on this. We're going to take then the Kw, which is 1 times 10 to the minus 14, and divided by the hydrogen ion concentration. Okay. Which means then it's going to be 1 times 10 to the minus 14 divided by 1.4. Whoops, sorry. Let me go ahead and clean this up a little bit. 1.4 times 10 to the minus 6. Okay, and we'll get our answer, and we should get the same answers. Let me go ahead and do that really quickly. So it's going to be 1 times 10 to the minus 14. Sorry, minus 14. 10 to the minus 14. This divided by 1.4 to the whoops, sorry, sorry guys, to the minus 6, and sure enough, I get 7.142857143 times 10 to the minus 9, or 7.1 times 10 to the minus 9 molar. Okay, so either way, folks, you guys will get the same answer. Either way, you'll get the same answer. Either way, then it's a 2-step calculation. Okay, either way will work. You choose how you want to do it. You can choose either to use the pKw and the relationship between pH and pOH, or you can use the Kw and the relationship between hydrogen ion and hydroxide ion concentration. Okay, all right. So again, in either using either method, okay, hopefully you used one of the two. you're going to have to take 2 steps. It's going to be 2-step calculation in order to get your answer. Okay. All right. Very good. Let me go ahead then, and let's. If you have questions, please make sure you ask. Okay? All right. So with that said, with the time that I have remaining, okay, what I want to do is I want to get started into the discussion of equilibrium. So up until this point, we've talked about acids, we've talked about bases, we've talked about how we can calculate for the hydrogen ion concentration, hydroxide ion concentration, how we can determine whether you have an acid solution or a base solution. So that was basically background information. We really didn't talk about equilibrium yet. What I want to do from here on out, so for the rest of the chapter, then we're going to focus our attention on applying what we learned in chapter 13 about equilibrium to acid-base chemistry. And so that means that we're going to do acid-base, we're going to do equilibrium, and we're going to apply it to acid and base, acids and bases. Okay? And so to get that done, whoops, oh, there it is. Anyway, to get that done, then what you're going to have to do then is there are a few steps that you have to take. Okay, before you set up the ice table. So we're going to set up the ice tables again. So before you do that, okay, there's a few things you want to make sure you do. You want to make sure that you identify what's happening in the reaction. Okay? First of all, you have to identify what the reaction is. Okay? And then what happens to that reaction as a result of you adding a certain amount of hydrogen acid or a certain amount of base. Okay? So you want to be able to identify what the major species are that are in the solution when equilibrium is reached. I'll talk about what this idea of major species is. I'll talk about what they are, but basically what are the components of the reaction that are in solution at equilibrium? What's floating around in the solution when equilibrium is reached? Okay? And so at that point, then once you have that, you can go ahead and you can solve for the pH. Okay? All right. So let's go ahead, and so that's basically the steps you want to consider first and foremost. Okay, you want to talk about that. We want to be able to practice that first before we even talk about equilibrium. We have to deal with this whole idea of major species and what's going on. Okay, so let me go ahead then. Let's do an example. Okay, all right. So we have a solution here of hydrochloric acid. We have a solution of hydrochloric acid. Okay. Now, let's consider first and foremost what's going on when we add hydrochloric acid into water, okay? Or an aqueous solution of hydrochloric acid. And we did this today. We did this today in class where I asked you if you take this acid here and we deal with the autoionization of water. So what we're doing here is we're going to take this acid that is already aqueous, okay, and we add it to water, which is liquid. Okay, we will form then a reaction or process in which the hydronium ion forms, okay, and the chloride ion forms as an aqueous solution. Okay, all right. And so based on this, then we were able to find then the Ka for this solution then as being the hydronium ion concentration times the chloride ion concentration all over the concentration of hydrochloric acid. Okay. All right. So what you need to make sure you're clear on this, and this is where you need to go back and you need to identify or remember, you're supposed to memorize the table of strong acids and strong bases. Okay. You're supposed to take a look at this and you're supposed to recognize then, first and foremost, that HCl, hydrochloric acid, HCl, is a very strong acid, which means then that when it dissociates completely into hydrogen ions and chloride ions. There's nothing left of for the most part, there's nothing left of the HCl intact. You don't have HCl together. Whenever you add HCl in water, it separates. It tends to separate. It's a very strong acid. It's a very strong electrolyte. So you end up with hydrogen ions and you end up with chloride ions. You don't have any HCl left over, which means then if that is the case, Ka for this solution then essentially then will be hydronium ion and chloride ion without the presence of HCl. Okay, without the presence of HCl. Okay, which means that if you have this in solution, okay, what are the major species floating around in solution at this point? Well, you're going to have a lot of hydrogen ions floating around. You're going to have a bunch of those floating around. You're going to have a bunch of chloride ions floating around. Hydrogen ion meaning that you got a bunch of hydronium ions. Okay, so essentially what you're going to see here then, you're going to see the hydrogen ion being represented. Okay, so you have then hydrogen ions here. That's basically it's going to partner up with the water and the chloride ion. You have a bunch of that, and on top of that, then you will have water molecules. and you will have a bunch of water molecules floating around as well. Okay. All right. So with that said, how do you go about calculating for the pH of the solution? How do you find the pH of the solution? Well, we have to consider one other process. So this is one, that's what's happening inside when you add HCl. But remember, water also ionizes. Okay, so I'm going to write it this way here. Auto ionizes, okay, to form then hydrogen ion. I'm sorry, let me go and do this. Two waters form then hydronium ions and okay, and hydroxide. Okay. So make sure you understand then that in this process here, the concentration of hydronium ions is going to be 1 times 10 to the minus 7. The concentration of hydroxide ion is going to be 1 times 10 to the minus 7. Okay? And so make sure you understand then, and I'm going to write the auto ionization of water in this manner here, the shortcut way to get you to see this. Okay? And that is then when water self-ionizes, it's going to form then hydrogen ions and hydroxide ions to a very small extent. So when we compare this equilibrium to this one here, hopefully you see then that the amount of hydrogen ion that's floating around in solution comes from the hydrochloric acid here. Okay? So that means then the concentration that you have of hydrogen ions when this dissociates, when you have a 2.0 times 10 to the minus 3 molar solution of hydrochloric acid, you're going to end up then with a concentration of a hydrogen ion that is 2.0 times 10 to the minus 3 molar. Okay? So you have from this dissociation, this much hydrogen ion floating around. You have from this dissociation, you only have 1 times 10 to the minus 7. Okay? So the contribution, the hydrogen ions that come from, that's floating around, comes from this dissociation here, not from this one, not from the auto ionization of water. And so therefore, if we're going to calculate for the pH, which is the negative log of the hydrogen ion concentration, okay, you would do this. Now, some of you would argue, well, don't we just add it together? Isn't the total number, isn't the total amount of hydrogen ions the amount of hydrogen ions from this dissociation plus the hydrogen ion from this dissociation? And my answer for those of you folks who are thinking about it that way is you are absolutely right. You are absolutely correct. That is, we should add these two hydrogen ion concentrations together. But because this is so much larger than this, you can go ahead, you can add this number right here. You can add 1 times 10 to the minus 7 to 2 times 0, 2.0 to 10 to the minus 3. And you're going to essentially get 2 times 10 to the minus 3. Because this number here is almost 10,000 times smaller than this number right here. This is a huge number. Okay? And so that's why then we can approximate. And that's what we're doing here. We're approximating and saying then that all of the hydrogen ions that come from the, adding hydrochloric acid into water comes from this solution. Okay, so with that said, then we can take the hydrogen ion concentration from the hydrogen ion, okay, from hydrochloric acid, plug that in, okay, and we'll get our pH then. I get the pH here as a 2.70 as our final answer. Okay, so that is the pH for this solution. Okay, the pH for this solution then is based upon this dissociation here. Okay, all right, let's go ahead then. And what I would like you to do, and let's take a look at this. I would like you to do, let me go ahead and clear this up. Let's take a look at whoops, major species. There it is. pH then, there it is. I would like you to try number 11. With the 2 minutes that we have left, what I'd like you to do is I would like you to get started on number 11 here. Okay, get started number 11. And what we'll do then is on Thursday, I'm going to start with this problem here. I want you to hold on to your number 11. I want you to hold on to your work for this one. And then what I would like you to do is on Thursday, let's compare our answers. Okay, so we're going to finish up with this problem. I would like you to post your work for this problem as well on Classroom. But we will start with this problem on Thursday, and then let's compare answers. So what I'd like you to do here, for a solution of hydrochloric acid that has a concentration of 1.5 times 10 to the minus 11, I'd like you to calculate for the pH for this solution. Okay. All right. Good luck with it, and let's see what you come up with when you work this out. Okay. I will see you folks on Thursday. Please make sure you watch the video, okay, and come with your questions on Thursday. Okay. Have a good day, you guys, and I will see you. Have a good Wednesday. And I will see you on Thursday. Okay, see you.